Okay, then for me it's a pleasure to introduce to Jakub Koncki. He's going to talk about how to compute higher term polynomials of multisingularities.
Thank you. Thank you very much for the possibility to give a talk. I would like to tell you about a joint project with Richard Rimanyi about computing higher term polynomials of singularities. So there are many experts in the topic here, but let me nevertheless give some basic definitions. So I will consider two positive integers, L and N, and a given germ of a map from C to M, and from C to M, 0 to C to M plus L, 0. Then, if we have a map between varieties of dimension, smooth varieties of dimension M and M plus L, then I can associate to it a set M eta of the points in which the map F has germ eta. M in M such that F has germ eta at M. Okay, this is intentionally a little vague because I don't want to go into technical problems. And I can also define set in the target, which is just the image of this one. Some polynomials give us a way to compute characteristic classes, such as fundamental class, of these two sets. So there is a polynomial called target polynomial of eta. Okay, and this is polynomial in rings of there are infinitely many variables indexed by C1, C2, C3, and so on. And if we make substitution, Ci goes to Chern class of pullback of tangent bundle of the codomain minus tangent bundle of the domain, then we want to have that this class after the substitution is equal to the fundamental class of the closure of our set. If by F in brackets, I mean that I exactly make this substitution, and this holds if the map F is nice enough. I don't want to say what nice enough means. Okay, this is very nice result especially when this set is finite, because then we can just say how many points it has, computing some polynomials in Chern class.
Jakub, you called it target, but I think you want to call it source.
Yes, of course. Sorry. Yes, I can also take target one, which is polynomial in variables s lambda. Here I have one variable for every partition, and it's linear, such that it calculates the class of the image. Okay, and this other substitution is given by s lambda goes to push forward of C lambda of the same bundle f star Tn minus Tn, where this is just the product of Chern class. So actually, these two polynomials are the same. One monomial here corresponds to one variable here. Okay. So, but this calculates only fundamental classes. So there are several ideas how to generalize this. First, instead of fundamental class, take some more complicated characteristic class. I told you that this computes number of points if the set is finite, but if it's positively of positive dimension, maybe you want other characteristic. So it turns out that Segre-Schwarz-McPherson class is the proper generalization. And the second idea is that there are similar formulas, like this class computes how many singularities of a given type we have. But there are also formulas for multiple points, like how many double or triple points. And to put it in this framework, and this would be multisingularities. Okay, and this will be higher Thom polynomial. Okay. So let me start with this first part. This was introduced by Omoto. He showed that there is, and I will be in the for this time, that there is a power series in the same variables, which if we make exactly the same substitution, then we obtain Segre-Schwarz-McPherson class of M eta. And okay, here I need to be more careful, because here I just take closure, but here I can take function one on closure, one on the set, or maybe something in between. I will tell you precisely what function I take when I go to multisingularities. Like, let me be vague right now. I want some version of Segre class here. Okay, and of course, as Segre class is fundamental class plus higher order terms, then this polynomial is just the standard Thom polynomial, this plus higher order terms. So in the lowest non-zero gradation, this is exactly the classical Thom polynomial. Okay. And the second idea.
Maybe, I'm not sure if it's needed. Maybe you should record for some people what the Segre-McPherson class is. I know it, but
Okay.
Everyone knows it.
For me,
I know it. Hopefully, I want to check if I remember it correctly.
For me, Segre-McPherson class of X in Y is Chern-Schwarz-McPherson class of X. Okay, and I assume M, and I assume that N is smooth. Is to M, maybe by some class of identity on M. So this is just lambda y. No. This is just class of tangent boundaries. Just a class of tangent boundaries. Okay, so maybe I'll write this. This is CFM of X in M by total Chern of tangent boundaries. Thank you. Okay. And the second idea is to introduce multisingularities. So if we have multisingularity, for me will be just multiset of singularities, like n1 up to nk. I introduced some order, but it's needed. These things may be the same, like this is multiset, this is not just set. And to such a set, I can associate eta target set, which consists of these points in N, who has exactly k pre-images, f minus 1 of N equals x1 up to xk, and at these pre-images, we have exactly these singularities. and f has germ eta I at xi. Moreover, if we take multisingularity with distinguished element, okay, like R, eta 1 and 1, then we can associate a set in the source of these points such that the image lies in here. So f minus 1 of f of m has exactly k pre-images, and f has these germs at the pre-images. So f of m belongs to NO eta bar, and f has this distinguished singularity at m, and f has singularity eta 1 at m.
There's a typo. Small m is in big M, not a big N.
Big M, of course. Thank you. So, okay.
I don't understand the difference.
Okay, here there's a set in the target, in the source, here it's in the target. Here I say pre-image of this point has exactly this set of singularities. And here I said
And order. Right? The pre-image. You can order the pre-image in a way so that
Yes.
of course. It's not ordered.
Yes. And here I choose
one
distinguish, and I say that at this chosen point in the pre-image,
No.
I have. Thank
But
you.
sorry, and this doesn't see the relative position of the different branches, right?
Can you repeat?
This doesn't see the relative position. If I say regular and regular, it doesn't matter if they are like that or if they are tangent, right?
Okay, no, because I specify singularities here. So
In the source.
yeah. So for example, I can take, if I take a0 squared, it means that I have double point which is smooth on both.
Yes. But they can be tangent to each other. They can be two branches, two parabolas. They can be a line and a parabola like that. That would be a0 squared, right?
This is what we will consider only nice maps. Some transfers of the two. So that all this.
This is not
You will rule that out after.
Yeah, correct.
Okay.
At this point, this definition doesn't see that.
Like this, even this formula here works only for nice maps, right? When there is some transversality
maybe
condition.
write it F nice, and then you see it on the board.
Okay. Nice.
And then that accounts for everything.
Well, some transversality has to be assumed for common.
No,
And you see, nice is the reason why you need a select type class. Because here you pull back,
Yes.
you don't push forward. But
Yes, and we need this to be transversal to some stratification to be able to pull
I
back.
mean, this rules also.
I think there's another reason why we need sigma and not germ, because we want this to be independent on in what jet space you want to consider. Like, do you want it in 100 jet or 101 jet or 102 jet? I don't want the polynomial to depend on it. And let's gain the pullback property.
So Kazarian proposed a definition that there should be polynomial. Okay. Let's take the next one. There should be polynomial without this in source. Let's start with source. In both variables C and S, like C's are indexed by a natural number, but S's by partitions, such that if we do substitutions, then we obtain multisingularity, then we obtain fundamental class of this locus of the multisingularity closed. And there should be polynomial in target only in C, but this time, like here it was linear, here we need to drop linear, such that it computes the class in the target closed. And maybe it's important to note that if we take as eta, like our multisingularity, that's just single singularity, just eta bar equals eta 1, then this set does not coincide with this set here, because here we have additional assumption that f has exactly one pre-image. But the closures coincide. So on the level of fundamental classes, we have, that if eta bar is mono, then it does not depend if we consider this polynomial here or this polynomial here, we obtain the same. So for monosingularity, this polynomial does not depend on s variables, and this one is line. Okay, and we would like to combine these two ideas and consider Thom okay, and well, maybe one more thing. This was introduced by Kazarian, but he didn't prove that such polynomials exist. He just conjectured it, and they were studied later. And the proof that they exist is pretty new. It's due to Omoto and Berchi-Senesh. And now Omoto conjectured that such things also should exist for multisingularities. We don't have the proof that they exist for multisingularities, but we have, assuming that they exist, we have some methods how to calculate them and some structure how they behave. Okay. Great. Maybe this one should stay. So in the end of the day, I would like to have Thom polynomial of multisingularity in the source, which is power series in C's and S's, which computes Segre-Schwarz-McPherson of class of this, Thom eta of f equals SSM. And here I want really the function 1 on this set. And I would like, and this is obviously, yes, and the same in the target, which computes SSM of 1. Omoto suggested considering closed varieties or some combination of functions, but we have nice structure if we take just one on the open set. I think this is similar that, like, if we take Segre-Schwarz-McPherson of Schubert cell, it behaves better than Segre-Schwarz-McPherson of Schubert variety. Okay. So
it also means if you understand the pieces, you can understand the closure, but not the opposite.
Yes, yes.
Yeah, but not explicit. This is the easy direction. The other one is.
I'm not sure if this is. I'm not sure if this here we have like this frontier condition of this classification, like, because for Schubert variety, closure of a strata is union of strata. I'm not sure if this is true here. I hope, but
I think usually it's not true.
okay.
Did you even introduce what is strata for you?
Right.
Okay.
Pieces,
These are things for me, And I don't know if the closure of such thing is a union of such
You
thing.
don't know this is a smooth.
Even if you, so suppose these are Thom singularities, then it's not true, the frontier. Of course, you can say contact them.
Yeah,
I guess it's evenness.
But yeah, so there's several reasons to say directly work with this piece. It's just a decomposition, and it's natural to take the number 1 on piece of the decomposition.
But moreover, there will be structure, and the structure only holds for this.
Okay, so I would like to say first some words about structure, and then how to compute. Okay. So,
Maybe change the marker, please.
of course, thank you. Okay, and I would like to have everything smoothboard, but maybe this side. Okay, so maybe first I will give you classical structure which Kazarian proved for the non-higher, just standard Thom polynomials of multisingularities. And I will focus on the source case, on the target case. Target. In the target, these polynomials are polynomials in many variables, one for every partition. But it turns out they are fully determined by simpler objects. Like we can consider as eta equal being linear part of Thom polynomial of the multisingularity in the target. And Kazarian proved that these things fully determine Thom polynomials. First, if eta is just a single singularity, then Thom polynomial of this multisingularity is just this linear part. I told you about this. Here, if you have mono, then this thing is linear. And then we have recursion. If eta is eta 1 up to eta k, then Thom polynomial of eta equals the linear part plus sum over all subsets in the set 1, 2, 3 up to k, which are not the whole set as it contains 1. And I take linear part corresponding to partition, okay, I take only singularities which lie in I, and then I take Thom polynomial of the remaining of the eta k minus I. So maybe I will give example to show how these formulas work. Example.
Well, and you just need multiplication of these polynomials in the right.
Yes, of course, thank you. If we take eta bar equal just a0, smooth point, then by the first point we have as a0, Thom a0, target equals a0. If we take a0, then we have Thom a0 equals S linear part, S a0, and then there is only one subset. Okay, there's only one subset which is not one, which is contained in 1, 2, contains 1 and is not whole. It's the subset 1, and this is S a0 because 1 belongs and the first was a0 times Thom a0 target because the second was also a0. And using the first line, we obtain that this is SA0A0 plus SA0 squared. Maybe one more, just to be quick. Just quickly, if we take the free, then we obtain linear part plus, okay, what are the possible subsets? These are subsets. I is contained in 1, 2, 3, but not equal, and 1 belongs here. So it can be 1, 1, 2, or 1, 3. For 1, we obtain SA0, Thom A0 square, and for both of these, we obtain SA0 square, Thom A0. And plunging in this already computed things, we can finish the calculation. So this easier things allows us to compute all the Thom polynomials. Okay, but this induction, of course, don't work in the Segrest-Schwarz-McPherson case, because one can check that even the first point don't work. So if we take monosingularity, we will not have linear polynomial, we have just a polynomial. And to remedy this, yes, this one. We will consider simplest possible singularity, multisingularity, the empty one. In the fundamental class store, okay, so eta var equals empty. So if we consider the set, this can be considered only in the target, then these are n which don't belong to the image of M. So such points that don't have pre-image. So in the case of fundamental class, this was boring because this set is dense in the N. So fundamental class of closure of N was just 1. And the Thom polynomial of this multisingularity was 1. But in the case of SSM class, this is there is some big tail here, and this is some complicated class. So we'll call this master series. Sorry. Master series.
Is related to this master function?
No.
Okay. And I think I would like to.
Not really anything, but the key to understanding multisingularity is to understand the empty set.
Yeah. It's always the most complicated.
So it turns out that even this is not linear, but it's nearby. So theorem. First, they exist linear polynomial. Linear such that this thing is exponential of this linear series. X. And it turns out that this formula will not work. That will work if we divide everything but this exponential series. So 2.
So you take like a gradient, this is an exponential of the power series.
Yes.
It's a power series, yeah.
Yes.
Take
So we take
by
just
degree.
yes, because we can in a single degree, there are only finitely many, so this is nice definition, so it works. Okay? And here, okay, to have this, we really need L greater equal 1. So this is like we have this map from M to M to N to M plus L, and I actually want this thing to start with 1, so I want the image to be, okay, so I want this set to be dense. So I really need the fact that L is greater equal 1. Okay, so we generalize this definition of Kazarian types, saying that for a multisingularity, this residual polynomial is a linear part of quotient by this master series. Tilde, thank you. And then, okay, this is 1, this is definition, and this is 2. And then we can just copy these 2 points. So if n is mono, then n bar is mono. And then target for Thom polynomials of this single multisingularity is exponent master series times this linear thing. And for arbitrary, okay, this is n equals n1. For arbitrary n, we have induction, just like it is here, which says that higher Thom polynomial of this multisingularity is master series times linear part plus, and I just copy the second part, sum over 1 in I sigma non equal n I Thom target and k minus I. So if we would like to compute examples here, in the end we'll get the same formula on this side, but multiplied by this master series. So
the SMT is always a common factor.
yes, but this is okay. This starts with 1, so we can. So there's no divisibility by this thing because this is unique, right? But
yes, it doesn't. Yeah, I see.
So
I can divide it by.
yeah,
Everything is divisible.
Yeah.
Very good for this.
but the trick is that if you divide by this, it will look nicer because these things are linear. So instead of computing some hard polynomial, we just compute linear one, which should be much easier. Okay? So for A0, we get.
Is the formula nicer if you take x over SMT as a common factor?
Can you repeat?
So if you take x of SMT as a common factor, which you can always do, but is the formula nicer?
As a common factor in what sense?
You lose linearity.
Yes.
So these are just linear maps. So for every partition, you need a number. So these are the things that we like. If you multiply with the Smith series, then it will be a huge mass of those things multiplied with each other and creating a polynomial.
No, but I was thinking it's like log of 2. If you just like multiply 2 by x of SMT, it seems to be this. Log of 2 on the next.
Okay, so
Maybe
this.
Yeah.
Okay, so here if you divide everything by x of s empty, then you have exactly this formula but for Thom divided by Thom for f. So this holds if you substitute instead of this. So in the end, you get that for a0, you forget a0 times sa0, and for the double one, you get x of s empty times exactly the thing you get there, s tilde a0 square, a0 plus sa0 square. Okay. Just sorry.
Stolen it.
Sorry. And this polynomial in the lowest degree are exactly the polynomial from here. Like these are power series, not like s's were polynomials. These are power series, but in the lowest degree they are the same. Okay. So did I want to add something here? Okay. So maybe in a minute I will go to computation, and I would try to convince you that it's easier to compute single such thing at a time to compute full Thom polynomial than to computing Thom polynomial, because this is linear and this is not. As I told you before, these polynomials, we don't have proof of existence, but if you look at the Toru work, he actually used this Kazarian formula in his proof of existence of Thom polynomial of multisingularity. So we hope that that structure may help in the future in the proof of existence.
Sorry, I don't see the difference between the two blue lines. In the examples that you gave,
Yes?
these two guys,
Okay.
on the left, I see the same thing. Okay.
Sorry.
Yeah.
Yes, I forget about tilde all the time. Sorry.
Okay. The black thing is the first degree approximation, so that's a formal power series, and what's on the right hand side is just the lowest degree part.
Okay. So I would like to tell you what is a standard way to compute such things in low degrees.
So, do you want to say anything why it works in this way? So, for example, for me, what is the reason that you should write it as x of something? So, I would expect that x is popping up because how it behaves in disjoint union is usually
Yes.
the reason.
Yes, exactly. We studied the disjoint union, and one can prove that under some assumptions, we have tilde. We have such behavior like this on the level of variables. This means sum the variable, and okay, if we logarithm, we just obtain linear behavior.
Yeah, but okay, that goes in the direction I know why x should pop up in form of these kind of things. Yeah, okay, that's good.
And maybe one more if you ask.
Sorry. There's something I don't understand. I see 2 times the same thing on the left, and then on the right side it's different.
Wait, where?
In the blue.
A0, A0.
You missed
The bottom
The
line.
second one is A0.
on the left side. You missed an index.
Yeah, okay.
Oh, of
A0
course.
is right. Oh, yeah.
Sorry.
Sorry.
Yes, my bad.
Just a test.
Yeah, no, that makes sense. Yeah.
Okay. I think maybe I don't want to give a proof, but maybe one intuition why this is the right thing to consider is in the proof you consider some power series of the in the proof in the fundamental path case. You consider the power series of the form t a0 to some power t to k. Okay, maybe Just this one. Maybe I want m of eta of a0. So power series, when I take fundamental classes for longer and longer singularities. And it's really important that this power series starts with 1. Like if we take k equals 0, then we obtain fundamental class of everything, so it's 1. But if we change this to SSM classes, then I get SSM of m, I call this n of empty set, I think, plus SSM of m of a0, t, plus, and so on. And this is definitely not 1. So I just divide everything by this first element to obtain the power series, which starts with 1, and then I can do similar proof than Kazarian. So this is the reason why I need to divide everything by this exponential. So now I want to say a few words about interpolation method. Maybe this one. So I don't want to give precise definition, maybe more an example. So if you want to compute Thom polynomial, then the method first say we want to compute just Thom polynomial of single singularity. The interpolation method says first find the degree of Thom eta, and there is formula for this part. Then write the general form. And here I will like to be in source. For example, if degree is equal to, then codimension. Then every such polynomial is a times c1 squared plus b times c2. And we only need to compute these two coefficients. Okay? If you want SSM, this becomes much more painful, because then there is degree free part and so on, plus and so on. And Richard proved that there is a finite collection of maps which allows to compute these polynomials up to some degree. Like we have some test maps, right? For every degree. For every degree, we have test maps. F I vi to wi, and we check. Oh, sorry, if the defining definition of some polynomials works for these maps. And it turns out that we can compute these coefficients just from our test set of maps.
And you know who these guys are exactly, or
yes,
or you know that they exist?
Okay. The bad part is that they exist only for small dimensions, like for up to 10 or something. But we know exactly who these guys are. So, but there is a problem. It's easy to compute. Okay, you get the formulas like, for example, for this fundamental class of the set VE with singularity eta equals a c1 square of eta plus b c2 of eta of fi. And in general, this side is easy to compute. There is a way to compute this side, but this side may be very complicated. Like for fundamental class, actually you can take, for fundamental class you have only maps such that this thing is either 0 or a single point, which is very nice. But if you want to SSM and you need higher degrees, then you get here SSM of some very complicated set. And this is a problem. And there is idea coming from work of Okunkov, which allows to fully omit this problem, like to don't compute any geometry of this set of singular points at all. Okay, maybe. How much time do I have? Do I need to? Yes, I have time. Great.
Can you put some type of fake total section? Can you put some fake total section?
Yes,
exactly. Terms that can localize.
These are already lots of symmetries there. But locally, there's a different idea needed.
Okay, so Okunkov and Maulik define stable envelopes. This is some cohomological class, and it turns out that they have three axioms. They define it by as unique element which satisfies three axioms. This is support axiom. Okay, this is some element in equivariant cohomology of something. Support axiom, which tells that A restricted to some points equals 0. I'm very vague here. I don't want to be precise. There is normalization axiom, which says that A for some different point is given by precise formula. And also, there is smallness axiom, which means that for the top degree of A disappears. And it turns out that Chern-Schwarz-McPherson class satisfies, of some subset, satisfies this property. So in many cases, we have that if we have subset in linear space, torus acts on the linear space, and we consider Chern-Schwarz-McPherson class of X into V, then in equivariant cohomology of V, then under some assumptions on X, definitely I want 0 does not belong to X, and conical probably. The top part disappears. The top part is equal to 0. And it turns out that this is the only information here which is needed. Like we'll have, if the set is nasty, we forget everything about lower degrees. It is possible to prove that the top degree disappears, and if we restrict, give only equation which tells top degree disappears, this is enough to compute all coefficients. So in fact, we don't need to compute all this class. We just say top degree is 0. So okay. Okay. This is okay.
Are you putting some extra assumptions here?
Yes. I think 0 and X is.
No, but you have to define a total section first. That was great.
Yes, I have.
But that was, I thought that this is some general statement. Now you want to define a torus action on these germs.
Okay. So I will need to tell you what are Fi. So Fi are prototypes of singularities, and there is action of maximal torus of automorphism group of singularities. And actually, I take this equation in equivalent cohomology with respect to this torus action, and then I can play exactly this game. Then these two things are really linear spaces, and everything works. So for
So Fi is like a general linear projection. What is Fi? So Vi and Wi are two linear spaces. Fi is some.
okay, we take
There's a prototype of singularities.
eta, which is monosingularity, and there is some stable map F Cn Ca0 Cn0 Fi Cm plus L0. This is eta. This is stable map of minimal dimension, like for minimal m, and this is exactly our Fi. And
And this will be equivariant with respect to the torus.
yes. But
So you would have to have the vanishing you asked, like guided by Koncki's axioms. Of course, you apply to the Kern-Schwarz-McPherson term.
yes,
For the applications, you would like to move to the sacred type classes.
yes,
But since you are going to the fundamental class, you just multiply by 1. So if you have it for the 1, you have it for the.
no. We actually give a formula. We have the formula that SSM of VEN divided by CSM divided by churn of VE equals our polynomial. Let it be here. So but we know this. So we multiply here, and
So
we get some messy equation. But this can be done by computer, like
yeah, because the other player is explicit. Yeah.
yes. So
And to answer Leonardo, so the vanishing of the top degree is trivial from your point of view, just because 0 is not in X. So the top degree would measure the Euler characteristic, but 0 is cut out.
Sure. Yeah, but there is some constraint here, right? I mean, all these test maps have to be equivariant. So you have to be able to prove that they exist in an equivariant setting. So the variables need to.
It is a miracle of singularity theory
Right. So
that all the singularities in the so-called nice dimensions have enough symmetries. That's just an experimental fact. God created the right way. So all of these just work.
Stable ones, right?
Stable.
This is the nice ones.
The nice ones.
the stable ones are all also torus stable.
They are
Symmetric.
So it's more than that. They have enough symmetry so that some Euler classes are non-zero, so that the gluing construction works.
and maybe I would like to say also that okay, this is done for monosingularity by Richard and will be soon be on archive, and we have all this also for multisingularity, and for monosingularity. Okay, you need to check here for. It turns out that this this theorem which was on this table about the structure actually allows to throw, so to get smaller set of maps. Like you don't need, because you normally need not also germs of monosingularity, but also germs of multisingularity. But actually this is hidden in this induction. So if you have induction at the beginning and you are computing this residual polynomial, this S's, then you can compute only for monosingularities, and this is much bigger.
So one question or comment maybe. So you want to have this vanishing degree which comes from because the compound 0 does not belong to X. So maybe that relates also why you should take not closures of sets, I think. Yeah? Then we will destroy this.
Exactly.
This property.
Exactly.
Okay.
Zero should not be only closure.
No.
No.
That's a good thing. There's not in the set. It's not in the closure.
Take a cone cutout 0, it's CSM plus top degree 0.
If I take this, the CSM class of the empty sugar cell, that contains 1. If I localize that thing at 1, it's 1. It's not 0. So you take, you localize the CSM class at empty set at any point. It's going to be non-zero.
No, but if you take TSM class of sugar cell and restrict to the point in the boundary,
Yes.
then you obtain something which is 0 in top degree. Which is not 0, but it is.
Yes, if that sugar cell is the open cell,
Yes.
then it's not going to be 0 in top degree.
It will be 0.
I've done something.
It will.
No, okay. It will be divisible
You have to be
by.
careful. This is a homological index. So what
Yeah.
degree is homological degree 0.
Anyway, we can
We
check.
can discuss
Yes,
that.
yes. I will let it on.
Oh, that's a discussion afterwards.
This is a thesis.
Oh yes, I have 4 minutes, so I would like to. I will not give you. There are okay. I presented you the formulas in the target. Kazarian has also formulas in the source, and we can also generalize those to the higher Thom polynomials, but I don't have time. I would like to present to you also the master series for L equals 1 up to degree 5, and you can see that it gets rather nasty quickly. We would really like to understand some structure here, and we computed this for up to degree 9, I think. Okay, and some parts I understand, like this minus 1, 1, 2, minus 1/3, 1, 4, 1/5. I understand. I can give explicit formula why they are here.
Did you find the pattern?
I understand what you find.
Okay, and also for 1, 2, and as many ones as you want, there is also nice formula. But then there we get these nasty things like 7/6, 29/30, and so on. I can show there's evidently some regularity which can be observed, but we cannot prove. For example, if we take this degree 4 and we sum these three things, we obtain 0. And the same is true in degrees 6 and 8. So we hope that in every even degree, starting with 4, they sum to 0, but we don't know why. You may also look at the coefficients with,
But not in degree 2.
but not in degree 2. In degree 2 we have 1/2. I don't know. But in 8, this is like really long expression, and it's magic that it sums to 0. Okay, if we take S2 as coefficient near S2 and S4, we get 7/6. Then there is 29/30, and if we take then for 6, we get 33/32, and you can see that this is 1 plus Bernoulli number. So this is 1 plus, I think, B2, 1 plus B3, 1 plus B4, and I have no idea why Bernoulli numbers occur here. Oh, I don't remember, but it was. It still fits. But and then we cannot compute further, so if you have any idea of how to find regularity, it would be great. We can also say if we go with L upstairs, then this slowly stabilizes. Like single coefficients stabilizes at maximal number which occurs in partition +1. And the limit is very easy, a limit we can compute. But it will be nice to see what happens if we change L by 1. For example, for standard Thom polynomial, there's result by Sahel and Rimanyi, which allows to compute Thom polynomial for smaller L from Thom polynomial for higher L. But here we using something called decreasing the operator, but here we cannot even define this operator. So this is hard. I think this is all. Thank you.